Hi everyone, welcome to the Lifecycle working group. Today is September 22nd, and we have one item on the agenda. It's a presentation from Daniel, Node Lifecycle at Datadog. So firstly, would like anyone to introduce themselves? Okay, I guess we can just get straight to the presentation. I presume you would like to have sharing, so I will share it now.
This would be great, yeah. Okay, let's see if the magic works. You should see the slides now, right?
Yes.
Perfect, cool. Okay, then I will start. Hello, my name is Daniel. I'm working at Datadog, and with me here in the room are Caitlin and Raoul, who are working on the project too. And I wanted to give you like an overview of how we are handling node lifecycle management at Datadog. We've been working at this project for the past, I think it's like 4 years now. And it works pretty well overall. And I saw that there are some differences to other systems we've been hearing about recently. So first of all, to give you some context about our infrastructure, this is a slide that you will see in all of our presentations, but we are running like thousands of clusters which have like multiple thousand nodes each. And all of these are run in many different cloud providers. So the solution we wanted to build should be, let's say, working everywhere, no matter what's underlying. However, it's always cloud-based, so we don't have any on-premise infrastructure or something like this. So when we are talking about node maintenance, what we are usually doing is just replacing the node. So instead of taking a node out of rotation, doing some updates and then putting it back, we will always just drain it and shut it down. The system works very well. Like 99.4% of all of our nodes are covered by the system and will be rotating all the nodes. And this leads to having multiple thousands replacements every single day. And this includes everything. Like we have one single system and one single platform for stateful applications like Kafka, Cassandra, and many other databases, as well as our stateless applications like APIs. There are some triggers that are triggering the node replacement process. And here are some, let's say basic categories. So we are usually trying to react to hardware failures, like if a node has disk issues or if there are some problems with the CPU, we want to get rid of the node as fast as possible. Besides this, there are some cloud provider specific things like VM retirements. We are also using the system for software updates of the nodes. Like we had a pretty bad incident a couple of years ago where we did like in-place upgrades of the nodes software. And after this, we decided to completely rely on our node lifecycle automation system. So instead of doing like an in-place upgrade, we are now draining the node, shutting it down, and creating a new one with the new version of the image that has the upgraded software. And finally, like optimizing some costs. So if we see that there are better instances to run this specific application, we will tag it, it will replace the instance, and a new type, a new instance with a new type will be created. So here's some, let's say, small representation from one of our Kubernetes upgrades. On the top, you can see like the last version and the new version. So this is the number of nodes by version. And on the bottom, you can see how many nodes were drained by our system. And yeah, there's a strong correlation between how we are performing cluster upgrades and how many nodes are being drained. So we are using the system for all these kind of things. While designing it, or at least while recreating it like 2 years ago, we kept some key concepts in mind that we wanted to always do, let's say. The first one is we don't want to have any maintenance windows. Like as we are running in the clouds, there's always a chance that something is happening to your VM. Cloud providers can just randomly shut them down. Maybe the instances are breaking. So you should never rely on having an instance for a certain amount of time. So designing our node lifecycle automation system should also not include any maintenance windows, because this would give the impression that you can rely on the underlying hardware as long as you're not in the maintenance window. Besides this, as I said before, like we wanted to have immutable nodes. So after a node is started and running, we don't want to install any dependencies on it. So in order to do software upgrades, we just want to replace them. So far, we've decided to not use any CRDs, and we fully rely on the eviction API and PDBs. I will go into more details later on how well this works, but so far we were able to sustain all of this with just the existing infrastructure. Important parts were that we wanted to make it as easy as possible to onboard. Like if a new application is deployed to our clusters, it should be automatically part of NLA, because it's without having any of the users implement any code. Like when you're just using a normal deployment, for example, it just work. And this also means that we don't want to have any human interaction. So it should be automatic in any case. And yeah, the last one here is we want to leverage Datadog itself as a way to monitor the health of the nodes. And what this means, I will go into details later. And the most important thing is that we want to do all of this carefully. So with everything we are implementing, we want to ensure that we are not causing any incidents. So if we are rotating any stateful application, it should be as careful as possible so that we don't lose any data, that teams are not paged at the night, and so on. So in the recent, I think I'm with Datadog like for 3 years now, and in all this time we haven't had any incident that was caused by our node lifecycle system, even though we are replacing multiple thousand nodes a day. So how does it look like? So I wanted to give like an overview of the components that are involved. This is like what Kubernetes is offering, right? We have the eviction API, which is taking into account the PDB status and checking how many pods are disruptible for your pod disruption budget. And if the PDB is fine, the pod will be terminated, and then at some point the cluster autoscaler will shut down the node because it's empty. And then we have the controller manager that is maintaining the status depending on the state of the pods. The first component is our drain controller. We've been using an open source project called Draino for a while. And then at some point we have completely redesigned the application. And the drain controller takes into account all nodes with certain conditions, and then it will taint these nodes and drain them via the eviction API. To get conditions on the node, we have a project called Node Problem Detector. It's somewhat similar to the open source project, but it's different in the sense that it's not a daemon set anymore. So our node problem detector is a deployment that has a couple of replicas in every cluster, and it's getting the node health via the Datadog product. I will go into more of these details later, but yeah, overall, if you have an alert for your node, the node problem detector is able to set a condition to a node, and this will trigger the whole cycle. And finally, we have an application called Disruption Budget Manager, which is basically filling some gaps that we saw on PDB level. It's implementing an admission webhook where we have more control about the eviction API. It will update the PDB spec depending on certain attributes and depending on the environment and much more. So how does it work in more details? This is like a overview of the system. You can see on the left that there are some notifications that will add the condition to the node. And these notifications are coming from certain areas. Like it can be coming from Datadog alerting system. Users can add them manually or other things. Like there is no limit on how these conditions can be added to the node. Our drain controller or our drain loop works like this. Like it starts with getting all the nodes with a certain condition. It will group them based on some stuff, which I will show afterwards. Then it will be sorted, and it will have like a loop that is going around the sorted list of nodes and just trying to figure out which one can be drained based on priority. And this can be drained is like a simulation. So it will check all the pods running on these nodes and their PDBs. And if one of them can be drained, it will go on, drain the node, and then we will start from the beginning. So how do we add conditions in general? So you can see here on the right a picture of a monitor. A monitor is like Datadog's alerting product. You can use all the data that is available in the product, like logs, metrics, I don't know, security things. You can use everything you want. And you just have to make sure that it has a node attached as a tag, for example. So in this case, you can see it's by host, and it has some tags here on the top. And with this, the node problem detector is able to connect the status of the monitor with the node. And as soon as the monitor is triggering or firing, then the node problem detector will add the condition, and this will trigger the whole node lifecycle automation. On the bottom, you can see an example of our kubectl plugin. We have built one called NLA, and there we have some common commands implemented that are useful for our users. So what happens, for example, is that if users are seeing that we have issues for a specific node, maybe there are some networking problems or disk problems, they can manually tag the node to be drained, and then the system will take over. From there, we are going into the whole node selection area, and this consists of 3 parts. So the goal of this node selection is that we will figure out which is the next highest priority node that should be drained now. And it consists of 3 parts. The first is filtering and grouping. So we are only looking for nodes with conditions, and then we are grouping them together based on certain labels. After this, we have a list of all the nodes that should be drained now, and then we are sorting them by priority. And finally, we will go through them one by one from the beginning to the end and find the first one that is evictable right now with the highest priority. And going back to this slide from the beginning, we have like certain priorities for certain conditions. And this will allow us to react to hardware failures or before optimizing VM type mix, even though the condition of this one was added way before. Let's go through a quick example. Let's say we have these 9 nodes in our cluster. There might be more, but all of these have conditions with different priorities. And they also have a age attached and a label. And what you can see is that some of them have label A and some of them have label B. So first, the system will filter out just the nodes that have a condition, which is all of them right now. And after this, it will select only the ones that are matching a certain label. And these will be then combined to something we call a drain group. So in this case, there will be a drain group for label A and a drain group for label B. And the idea is that nodes within this group are belonging together. So we should not drain too many nodes of the same group in parallel. But we can drain multiple nodes. So we can drain one node per group in parallel because they are not belonging together and they don't share anything with each other. From here, so these are the nodes here on the bottom right, just in a list. From here, we are grouping and sorting them by priority. So what you can see is that we now have 3 groups, and each group is just a priority level. Like we have these 2 nodes that have priority 100, this with 50, and this with 10. And then in the next step, we are applying the next grouping and sorting mechanism. So we are creating subgroups within this bigger one. And in this case, it's by age. So we will take the first group, which has 2 nodes, create 2 subgroups, and then order them based on the age. And with this, we can ensure that from the beginning of this whole mechanism to the end, we will have the highest priority for all these different steps as the first node in the list, and then the second highest priority as the second node. And the cool thing is that this is easily extendable. So if we say that maybe the condition priority is not the most important thing, maybe there's something else, we can just inject it before, then it will first take into account this more important thing, then it will do it by priority and then by age. And now as we have like this sorted list, we are going through this one by one and run simulation. So it will first use the one with priority 100 and 10 days. It's running the simulation, which is basically just it's iterating over all the pods and doing an eviction dry run. So we can figure out what happens if we would do a real drain right now, if it would succeed or not. In this case, it's not succeeding because one of the applications maybe has issues, maybe there's an ongoing deployment or something like this. So we will go on to the next node, which is drainable, and then we will just select it. So the next drain in our group is node B. And the same, so the whole process will happen for the drain group with the label A in parallel. So there are multiple Go routines in the background that are doing this in parallel for all the groups we have. Now that we have a node selected, we are going through the training phase, and this consists in 3 parts too. So the first thing that is happening is something we call pre-activities. It's somewhat similar to the interceptors of the CAP. And the idea is that we give our users the possibility to run custom code before we are evicting their applications. So what can happen is that maybe for a stateful application, we are moving the data to a different node. Maybe we have to remove the pod from the database cluster or something like this. Or what's happening quite often is that we are pre-provisioning a new node before doing the actual eviction to remove the time a pod is pending. After all of these pre-activities are done, we are doing the actual eviction. And this is just calling the eviction API endpoint with all of the pods in parallel. And when this is done, the node is empty, it's tainted, so no new pods can be scheduled. And then after some points, the cluster autoscaler notices that it's not needed anymore, and it will finally shut it down. In the whole process, we are communicating the current state via taints. So there are 4 different steps we've been talking about. The first one is like eligible to be drained, which just means that the node has a condition and we know it will be drained at some point, but we don't know when. So we are adding this taint so that our users see it and they can also use it for scheduling. And by default, we are telling Kubernetes that it should prefer no schedule. So if there is a node that has capacity and no condition, then it should be preferred to schedule new pods. After the whole selection mechanism was executed, we are going to this candidate phase. So this means that we selected the node to be drained now, and we are starting the process of pre-activities and so on. So the candidate means that now the custom code has to run, and after all of this is done, we will go into the draining phase, which is doing all the evictions. And after this is done, we are in drained, and this means that this node should not go back to rotation. It will be shut down eventually. In our first iteration, we've been using the cordoning API instead of taints, which is doing more or less the same. But we saw that there are some problems, especially during incidents between it's some problems with understanding who was cordoning this node. Interesting, no? What can happen is that during an incident, a user will just cordon the node, and then they, I don't know, maybe want to understand what happened, so they will keep the node around. Maybe they want to uncordon it later. So that cordoning means like manual interaction for us. And if we are using cordoning for our NLA system, we can differentiate between these 2 states. So we decided to go for taints instead, which is also being used by other components like the cluster autoscaler, which is doing more or less the same thing. Yeah, I will stop here for a moment and see if there are any questions for the things that I said so far before going into more other features and problems we have today.
I have a couple, unless anyone wants to go first. So in the beginning, you said you don't use maintenance windows. What do you mean by that?
So usually, or what can happen, especially with stateful applications, is that you don't want to be, or you don't want the pods to be disrupted at any time. Like, for example, if you have an RDS database in AWS, you can define at what points AWS can do maintenance on these instances. And this helps you to schedule these kind of things to a time where you might have less users on your website, for example. And we don't want to have a mechanism like this where our users say that our pod can only be disrupted between midnight and 6 a.m. Because in theory, yeah.
Yeah, so you don't have like we saw before in the other presentations, like pods running for a month, for example, or like can you describe like what kind of applications are you running in your clusters?
Everything. Like we have stateless APIs, we have stateful databases like Cassandra, Postgres, Kafka. Everything is running in these clusters, and all of them are using the same system.
Yeah, I would like to return back to the cordoning versus tainting. Yeah, I don't know, like how long is still the presentation? Well, like how many questions should we ask?
So there are we are at slide 27 and it's going till 40. So there are 30 slides left.
Okay, so
I can also continue if you want, and we can do the rest.
yeah, so I will like just ask about the cordoning, like when we just discussed that. Yeah, so yeah, it's interesting to see like that you mentioned that like the cordon can conflict with like existing tools, and that tainting prevents that because you can basically define your own taints. Yeah, like we have been like like trying to use this feature in the non-maintenance cap, but I see it's a bit problematic. So, but the taints, like, did you have also like any issues with them? Like because like they are like basically a scheduling feature, so and not like a non-maintenance feature. So like if you like taint a node and then like you have an application that does not have like a specific toleration, but would still like to run, for example, during the maintenance. Like, did you have like any issues like that?
I would say maybe. So as we don't have any real maintenance, the case that you've described is not happening for us. So when we are going into this phase, we will get rid of the node completely. So the node will disappear and any application should go to a different node. What can happen is that sometimes we are using local storage of the node. And when we are going into this phase, and there is maybe a deployment happening at the same time, the pod running on the node we are going to drain is being recreated and can't be scheduled to the same node again because we now have the taint. And but the scheduler needs to put it on the node because the PVC is attached to it. And this is something we definitely saw. And our drain controller is looking for exactly these cases. And if it happens, we are canceling the drain and trying it again afterwards.
Okay, yeah, that's interesting. Yeah, I think it might be useful like to have like scheduling available in some capacity during the drains, like overall, not in your case, but I mean overall. Yeah.
Yeah.
So also do you like are you running also some daemon sets, and like did like what kind of daemon sets, and did you have issues with them?
Yes, we are running a couple of daemon sets. I wouldn't say there are any issues with the daemon sets specifically. During drain, we just ignore them. But we have other workloads that are more tricky. And it's usually about, let's say, job-based workloads or at least short-lived workloads. And these are a little bit harder to support. So what we are doing is during the draining phase. So let's say it like this: with job pods, we have the assumption that they will be terminated at some point. So for our node lifecycle system, we are just ignoring them, which means that in the draining phase, all the pods that are part of deployment, a stateful set, or so on, will be evicted and they will be scheduled to a new node. And job pods will be kept running until they are done, and then the cluster autoscaler will shut down the node. This works quite well until it doesn't. So sometimes we see jobs that are running for a month and then blocking the shutdown of this node. But these are more like edge cases that need to be worked on.
Okay, so you have like general understanding like of what kind of jobs are usually running and know that they will be short or kind of short-lived.
No, we let's say it like this: we don't know, and we don't want to know, to be honest. Sometimes people are getting creative, and that's a problem. So we have some cases where teams are misusing jobs because of, I don't know, certain reasons, and then they are long run and they are never going to finish, which is a problem. But overall, we want to keep the assumption that it's a short-lived thing that will disappear on its own. We are currently implementing some mechanisms to clean them up if they're there for too long, and maybe keeping the resources around. But in general, we don't care.
Okay, thanks. Yeah, I guess we can continue and leave the rest of the questions to the end.
Good, sounds good. Yeah, I want to talk about some features we've implemented over the past years. And one of them is definitely like excluding job pods, which I just explained. Another one is like our goal was that it's really easy to onboard on the system. So in best case, you're only deploying your applications and it will be part of NLA automatically and it will just work. And the biggest problem with this is that we still have this gap of needing the user to create a PDB. Because the PDB is like the main communication mechanism between our system and the health of the application. So in like normal Kubernetes world, every team would need to define their PDB, make it work properly, define proper disruption limits and everything, and then deploy it. But this is not scalable, especially if you want to onboard a couple of hundred or thousand applications. So at one point, we decided to just generate default PDBs. Like whenever there is a workload in our cluster that don't have any PDB attached, we will create a default with max unavailable one, which in theory means that only one replica of the deployment can be missing at any time. And this worked out quite well for us. We sometimes have like huge deployments of stateful sets with a couple of hundred replicas where having only one disruption is really slow. But for these cases, we are then asking these specific teams to create their own. Another problem, especially when creating these defaults, is that you might run into issues with overlapping. For example, if your team is creating two deployments in the same namespace that are using the same node pod label selector, creating default PDBs for them will lead to having two pod disruption budgets that are both covering the same pods. And this is something Kubernetes doesn't like. So if there are two of them, Kubernetes will always deny the eviction request. And therefore, we have some, let's say, bigger mechanism to ensure that our default PDBs are never overlapping. So when we are creating one, it's only covering pods of a specific deployment or a specific stateful set. And the last 2 points are specific to our infrastructure. Like we have, if I'm going back here, we have a distributed log and the Datadog monitors, so our alerting system. And both of them can be integrated into your pod disruption budget. So the idea is that if your monitor, your alerting system is triggering for your application, the pod disruption budget does not allow any disruptions. And the same for the distributed log. So this is usually used during deployments where the team says, while we are deploying our Kafka database, we don't want NLA to evict any or disrupt any workloads during that time. So they are taking the lock. The PDB will automatically deny any eviction request, and then after the deployment is done, they will release the lock and the PDB will work as normal. Another thing that we saw is, specific to our infrastructure is that we have some clusters that are spinning all the zones in a region of a cloud provider. And then we have clusters or one cluster per zone in a specific region. And this is due to having like different failure domains and having a more high available system. The problem is that applications are sometimes deployed in, let's say, in a less high available way than required because of cost reasons. So in a normal cluster, which spans across all the regions, you might have, for example, 6 replicas. And instead of you running 6 replicas per zone, they will split it into 2 replicas each. And then the network, the traffic is distributed between them. The problem is that NLA is only on cluster level. So it does not know how many disruptions are happening on the other 2 clusters, but the application is like more or less then between them. There was a KubeCon talk from Ilya at KubeCon a couple of years ago talking about something similar. And we have implemented something in our disruption budget manager that is basically like a shared state, more or less. So whenever we want to evict, for example, this replica in zone A, the disruption budget manager will ask the other instances of the other zones if a disruption is okay or not. And as you can see here, it will reach out to zone C. In zone C, the disruption allowed is 0. It will put back the result that there's no disruption allowed, and it will DBM on zone A will automatically deny the request. So with this, we have like a cross-cluster PDB implementation, more or less. And as I said, like all of this is still based on the pod disruption budget. So whenever our system tries to figure out if we can evict something, it will always go to the pod disruption budget as the main source of truth. And if our users want to block us or do something, it's always going through the PDB or the eviction API. Another thing that is quite handy, especially during incidents, is the possibility to block the whole system. So in certain cases, for example, if the cloud provider has issues spinning up new nodes, we don't want to evict workloads and get rid of nodes that are in the cluster right now. Or maybe the application has maybe too much traffic right now, and we should not disrupt any of the pods to not cause any incidents. And for these cases, we've created an eviction gate. So you can tell the system that for a specific set of nodes, node drain should be possible right now. Or maybe on the whole cluster level, NLA should not do anything. And this goes down to the pod level. So when a user knows that a specific pod shouldn't be evicted, then they can say this via our kubectl plugin. They can block a specific pods and block the drain, or they can go on deployment level. So NLA will be blocked for all the pods that are part of this specific deployment. And yeah, as I said in the beginning, like this is usually used during incidents just to ensure that we are not disrupting things when something is currently in an unhealthy state. And finally, we have many more features implemented around how we are managing and maybe rate limiting how many nodes we are taking down at a time. If you have questions about one of them, feel free to ask them in the end, but I'm not going into details around this. So in the last part, I would like to go into some of the limitations that we are seeing today. The system works very well overall, but we can definitely see some problems that needs to be solved eventually. The first thing is like the readiness probe. As I've said through the presentation, like PDBs are our main source of truth. And the problem is that the readiness probe is being used for two different things. Like on the one side, a pod being ready means that the pod can receive traffic. But on the other side, Kubernetes is also reusing it to say that the pod can be disrupted because it's ready. However, there are some applications that might want to receive traffic, but are still not disruptible. So internally, we have a case where it's a stateful application that should be able to serve user traffic, but in the background, it's still copying data from other nodes of the cluster. So if they say the pod is ready, it means that it can be disrupted, even though we don't have enough replicas of the same shard yet. However, we cannot remove it from, we need to have it serve traffic because otherwise the load might be too much for the other instances. And for this specific reason, we've created like an issue some time ago where we, let's say, more or less proposed having a third probe in Kubernetes, which is like a disruptible probe that lets us distinguish between these two states. So you can use the readiness probe to tell a system that we are able to serve traffic, and then you can use the disruptible probe to tell the system if it can be evicted or not. Another problem, or not problem, but something we noticed over time is that there are a lot of different things that are disrupting workloads, and many of them are working, and so it's not consistent how they are working. Like tape-based eviction, for example, is even though it has eviction in the name, it's using deletions under the hood. And this is sometimes a problem and sometimes not. So in many cases, we would like to use the guarantees, like more or less guarantees that the PDB is providing us to take decisions if we want to disrupt this pod now or not. But there are always like exceptions to the rule. Because for example, if there is tape-based eviction involved, sometimes it's okay to respect PDBs. In many cases, it's not because it has some underlying node problems. So it would be great if there is a way to have a streamlined process so that all of these are going through the same system, and then the system can decide if this is like high urgency now or not. And the last part, which you might have noticed in the beginning, is like our long tail of to-be-trained nodes. When we're coming back to this slide from the beginning, we can see that in the beginning of the whole process, it's super fast. We are draining a lot of nodes in the first amount of time, but then in the end, getting rid of the last nodes in the cluster is always a pain. And this is mostly because of PDB. And I think this is like what everyone is noticing when using pod disruption budgets. It's really easy for users to misconfigure it and then block the whole system. I think some other companies are having like a fallback mechanism that is just deleting pods after some time. So if your application is blocking this for too long, it will be just deleted, and this is how you get rid of this long tail. But we haven't done anything like this yet because we still want to be careful. Like in worst case, this was a real issue and we are now deleting a stateful workload and lose some customer data, which is not acceptable. So yeah, we need to think about how to solve this in a good way. And finally, I want to just leave some sentences on why we want to help with the working group. So overall, it's super cool to see that this is something we or someone is now taking care of, because node lifecycle automation is nothing that is there out of the box, and you have to do a lot of things to make it work. So we would like to just provide our experience of maintaining our system from the past 4 years now. And yeah, what I saw in many meetings is that we have like a slightly different setup than other companies that are using like on-demand capacity, on-premise capacity. And yeah, this presentation should is like a first step to show that there is different world with different ways of working. Another nice thing would be to replace a lot of our custom stuff, like deleting code on our side and replacing it with native Kubernetes capabilities would be amazing. And this also goes into the next point, like it would be cool if we can address some of our problems that we still have with native Kubernetes things at some point. And finally, like Kubernetes is an amazing product, and we happily use it for years now, and it just works great for us. So giving something back to the community and helping to extend the system and to make it even better is like a good thing overall. And that's it from my side. Do you have more questions?
Yeah, thanks a lot for the presentation. It was very nice to see your system. I suppose like we will try to help and bring some of the logic to Kubernetes, but you have like a pretty a lot of custom logic that probably cannot be all translated. Yeah, so like what you said in the beginning is that you aim like for like complete automation, but in the end you said like still you have some nodes that you have to resolve manually. Like, but is it like a big issue for you, or is it just like an afterthought that you'd have some problems a couple of times and
Yeah, so it's always a trade-off. I mean, in best case, we want to have all of this automated. Unfortunately, like if we want to be very careful, it's not possible. This is not providing any issues in general, like on our day-to-day operations, it's not a problem at all. But we can see this during mass trains, for example. Maybe we had one case where a node image needed some updates, so we had to rotate a lot of nodes to ensure that they're running a new version. And in these cases, we have these kind of problems where we need to have a look what's blocking right now, reach out to the teams to make them fix it. But yeah, this means that it's like a one per, I don't know, quarter or half a year thing. It's nothing we are struggling with every day.
yeah, that's good to hear. Yeah, I saw that you like work with PDBs a lot. So like one thing I noticed, like you said that you are using the default PDBs, and then you are also trying to drain as much as you can. Like, does this like conflict sometimes? Like that you have like you said you are using max available equals 1. So if the application is like in these drained groups, and you want to evict all of these. Like if like this, you said you prefer to like edit to every application. So does this like have problem?
Sometimes. So it definitely causes problems when multiple replicas of the same PDB are running on the same node. Because then if the first pod is being evicted, the PDB does not allow any disruptions for the other pod running on the same node. However, it's like a time thing. And then it depends on how fast the new replica is coming up and is being ready. So what usually happens is that we are evicting the first pod. The second one will be blocked for now, and we will just retry for some time. And during this time, the first pod will be scheduled on a new node, it will be ready, and then we can finally evict the second one. So we saw problems where this mechanism timed out, but it's not a huge problem at all. We see these cases once every, I don't know, weeks, and then on the second try it works.
Like, do you have some process for communicating these approaches to your users?
No, our users don't care about this.
Okay, so they are not involved in like the node lifecycle at all.
Not at all, no. And in best case. So for stateless workloads, it only depends on the velocity. Like by default, it's like one disruption at a time. Maybe if they're running a lot of replicas, they might want to increase it, and then it's just a matter of updating the PDB. But in general, no one cares about it, and it just works.
And what about the stateful applications? Or like you said, like you have, for example, also PDBs across multiple zones. Is that the case as well?
Yes. So the PDBs across multiple zones are also there by default. So our users don't have to configure anything. And then it depends on the workload. So some workloads are okay with being disrupted, and they have some mechanisms automatically to deregister from the cluster or maybe move data. So for example, if we use external volumes to host the data, it's not a problem at all, because then the pod is being disrupted, it will be scheduled to a new node, the volume will be attached to the new node, and it will just start as it used to be. In other cases where we have, for example, local data, so maybe some instances with NVMe disks attached, in these cases, we need to do something before, like at least deregistering the node from the cluster so that the new instance can come up and sync the data. And in these cases, application owners have to write some custom code. But it's like not a lot. It's just a couple of teams that are doing this, and that's mostly it.
Okay, you also mentioned you are using like the similar thing to like the interceptors, like some kind of pre-actions.
Yes.
So are you like mostly writing your team is writing these, or also it's only for some teams like in some small percentage of time?
Yeah, it's exactly the thing that I described before. Like when a team knows that they need to do something before a disruption is happening, then they will write a pre-activity, and it's just a hook in the process. So in this case, we are using where are we doing this? I think the node spec or the node metadata to communicate current state. So the application is watching for a certain state, and then it will execute the process, and afterwards we can go on.
Okay, oh, great. Yeah, I know we are running out of time, but I still have a couple of things. Yeah, so the first thing, like as you mentioned about the readiness probe limitations, yeah, that has been discussed, and it would be great to see this to be solved. I hope someone has capacity to work on that, and we can maybe discuss like the details of the cap or of the feature. And also the second thing you mentioned, like that's like the normal eviction is safe. Yeah, this is the slide. Then we have other termination mechanisms which are not safe. So I'm actually planning to like add a section to the eviction request cap to actually have an option in the future to like synchronize all of these termination mechanisms under one API, as you just mentioned. So I would like to also see that, but I don't know like what will be the like pushback from the community. But at least it's good to see like we have one company that would benefit from that. I suppose there is more, but we don't have like the data. Yeah, but this should be extended in the future, I think. So yeah, I will write the section and then we will see. And yeah, I think yeah, we are out of time unless you have some last remarks. Okay, thank you very much, and for everyone who came to this meeting. And this will be on YouTube, so like everyone else will see it there. Thanks all.
Ciao.
Bye.